Hello, everyone. Welcome to this talk. This is Kedar Namjoshi from Bell Labs, which is the research division of Nokia. And what I'm presenting is joint work with Sugol Gesi and Krishan Sabnani, who are from Johns Hopkins University. So this work is about network route reconfigurations. So reconfigurations happen all the time due to things like congestion, failures, maybe changes in security policies, and so forth. The challenge is to reconfigure a network as it continues to operate. So for any update method, this should be the first requirement, that the network stays functional throughout the update. And we call such methods on the fly. The second requirement comes about from the very limited memory at each router. So routers have expensive content addressable memories that are limited in size, so they can only hold a single set of rules. So what that means is that any update method should ideally just replace the current set of rules with the new set of rules, and we call that being in place. The third requirement is about correctness, and what should that mean? So there is a very nice paper at SIGCOMM in 2012 that proposed the following criterion, and it says that any packet throughout this update, it should only be routed through the current configuration or through the new configuration, but never by a mix of the two. And this makes a lot of sense because the current configuration and the new configuration have individually been analyzed and are well understood. And it's only this mixture of configurations that is not well understood. So if we can make sure that packet routes fall into one or the other, then that is a good thing. Now, it turns out that it's easy to meet any two out of these three requirements. So for instance, if we can shut down the network, then that update would be in place and consistent, but it would not be on the fly. The SIGCOMM paper in 2012 gave an algorithm that was on the fly and consistent, but it was not in place because it required a router to support both the current and the new configuration. And clearly, if you don't care about consistency, then you can just update routers any which way, and that would be on the fly and in place, but it won't be consistent. So the challenge is to do all three. And there's been a significant amount of work since the SIGCOMM 2012 paper, but all of these results and algorithms, they either weaken consistency or they require shutting down parts of the network, or they're not in place, or they need extra memory. And so our algorithm does all three. And as far as we know, it's the first one to do so. But there is a but. The algorithm may drop packets, and it does so only if accepting the packet would violate consistency. So experimentally, we see that packet drops reduce throughput by 10 to 20%. And interestingly, we can show that packet drops are unavoidable for any method, any update method that has all these three properties. So we can't reduce the 10 to 20 down to 0, but what we can do is to either avoid drops or limit packet drops through some amount of lightweight network and update analysis. And this is very much an active topic of research. So one of the really nice things about this algorithm is that it takes ideas that originate in distributed systems, in particular the Chandy-Lamport snapshot algorithm, and converts them to solve this very practical update problem in networking. So now in the rest of the talk, what I want to do is to give you a feel for both the problem and why it's fascinating and challenging, and also for the solution itself. So there are a number of details that I will be leaving out. I will be simplifying certain things, but all of that is in the paper. And so I hope what you see at the end of this talk is why the problem is fascinating and interesting and challenging altogether. So the problem, as we have alluded to, is with mixed configurations. So since we can't update the entire network in one shot, we have to update routers one at a time. So we have some routers turning green over here. So during the update, part of the network will be in its red configuration, that's the original one, and some of it would be converted over to the green configuration, which is the new one. And what that can do is, if the packet routes are not carefully controlled, is that you can have a packet that starts at this red router, goes to the green one, is then routed to a red router, which then goes to a green one, and so forth. So the path that the packet follows is not entirely red and it's not entirely green. And so we have no guarantees about what it can do. And so you will see concretely why this is a problem with this very simple network example. So we just have 4 nodes connected in a cycle. So I'm going to call them north, south, east, and west. The blue arrows represent the physical connections, and the little circles represent packets. Now you can configure this network in 2 different ways. So in the original configuration, the red configuration, any packet entering the network exits through the north node. In the green configuration, any packet entering the network exits through the south node. Okay? So now let's see how an update might proceed. So you start with the red configuration and a packet that's flowing through the network. So this packet goes through the red configuration until it reaches the north node. Now let's say at this point, the north node is updated. Now, without any further control of the update process, what would happen to this packet is that it will get sent to the west node. And what we have just done is to create a routing loop. Now, this routing loop did not exist in either the red or the green configurations. It's only there because of this mix-up of configurations that happened during the uncontrolled update. And so you might say, well, okay, the routing loop exists, but it's going to disappear in a while once all of the nodes turn green. And that's true. So in that sense, it's a benign problem. But the problems can be more severe. For instance, you can have a situation where packets are required to go through a firewall, but during the update process, temporarily, certain packets kind of bypass the firewall. They still get from point A to point B, they just do not go through the firewall. And that creates an opening for attackers. So we don't want those kinds of situations to exist at all. So now let's take a different view of this, this example computation. And that's the space-time view. And this comes from distributed systems. So we're starting to make that connection. So what the space-time view does is that it shows a timeline for each node in the network. And since the nodes are going to update in place, the initial events on the timeline will occur when the node is in its red configuration. Then it updates, which is the black bar, and then it proceeds along according to its green configuration. So now if you connect up all the update points, that defines a network state. So we want to say intuitively that the entire network has updated at this particular state. And this joining together of points is called a cut in distributed systems. Now let's see what happens. So we send the packet from west to south. I'm just replaying the original execution. The packet moves from south to east. So far, everything is good. And now we see the packet moves from east to north. It crosses the cut from left to right because the north node is already updated. Now the north node forwards the packet to west, closing the loop. And this time, this transmission crosses the cut again, but from right to left. So that suggests that these crossings are somehow a problem. And indeed they are. So you can see that the state defined by this cut is causally just impossible because the green packet has been received inside the cut, but it has not been sent yet. It is sent only outside the cut. So there's a causal impossibility here. Now, moreover, this cut is non-quiescent. And by that, I mean that there are packets in flight in the state. So the red packet from east to north is still in the channel in this network state. But now suppose that these problems did not occur, that you did not have any crossovers, that the cut was causally correct and it was quiescent. What that would imply is that all of the red transmissions stay on the left-hand side of the cut, and all of the green transmissions stay on the right-hand side of the cut. So the cut forms this clean separation between the green and the red. So packets originating on the red side only pass through the red configurations. Packets originating on the green side only pass through green configurations, and that gives us consistency. So what we need is a control mechanism to make sure that every cut is causally correct and quiescent. Every update cut is causally correct and quiescent. And we get that by adapting this beautiful, very surprising result from distributed systems, which is the distributed snapshot construction. So it's one of my favorite constructions. If you haven't read this paper, please do so. You'll enjoy it. So now to our algorithm, which you can see it's about causality. So it's called a causal update. So it uses a special control packet that's called a marker. And the marker sweeps through the network, changing, updating configurations as it goes. But it also has another important role to play, which is it makes sure that packets from the green side do not cross over to the red side and vice versa. And to make sure of that, we need some rules. So this is what the rules are. And I'm going to show you the rules by just illustrating how they work on the same example. So every node starts in the red state. We move packet along as before. Now the update controller sends markers to some initial set of nodes. So the marker is this orange triangle. It's arrived at the north node. On receiving a marker, a red node does three things, and this is really the heart of the algorithm. So it updates its configurations, configuration rules to green, so it turns green. It flags the input channel on which it has received this marker, and it forwards the marker to every output channel. So you'll see that happening here. Now, a green node must process all packets from an already flagged channel. So if it has received a marker, then it can start processing packets. So you'll see that here where a new packet enters through the west node and it's following the marker on its way to the south. So the south node updates, it processes the packet which exits, and the marker moves to the east node. But what of this little red packet that is sitting there on the east to north channel? Now, the north node should not process this packet because, as we have seen, that creates a routing loop. So the general rule is that a green node will drop all packets from unflagged channels. So it drops this red packet until it gets a marker, and then the channel turns green and it can start processing packets from its input. And at this point, the update has completed. All nodes are green. The routes are set up as in the green configuration, as you can see. So in terms of the update cut that I showed before, the dropping of packets ensures quiescence of the cut, and the way the marker propagates ensures that you don't get into these causality problems. Okay. And that's the correctness theorem that we show in the paper, that the update computation is equivalent to one whose update cut is quiescent and causally correct. And I'm just showing you what the computation looks like for the scenario that we just looked at. We also show impossibility, and we've already seen this dilemma where we have to decide whether to drop a packet or to forward it. And forwarding the packet leads to a consistency problem. And so the choice is to drop, and we show that that is required. But that's what the impossibility theorem says for any update method that is in place and on the fly. So now to experiments. We have more in the paper, but I'm just going to discuss the AT&T experiment. So the AT&T topology is a wide area network in the continental US that has about 150 switches. What we do is to update East Coast to West Coast route from the shortest to the second shortest path. That's a pretty arbitrary choice, but that's what we do. And you can see three things. So first, the baseline, which is no updates are taking place. That's how the throughput looks like. Now we start the update at 20 seconds. It's over by 40 seconds. So the update, you can see we have a choice of where to start the update. So if we start at the edges, the throughput loss is about 15%. If we start at, if we include some internal nodes as the starting points, then the throughput loss is much more. And so it doesn't really matter how we start or where we start in terms of correctness, but it does matter for performance. And it turns out that in all of our experiments, starting at the edge, which is kind of the natural thing to do, gave the best performance. And the drop was between 10 and 20%. And this is the update completion time. So the one shot is just a non-consistent, update propagated through the network. The other two bars represent these two choices. Now you can see that there is an overhead in time, but it is not, too much. And theoretically, we can see that the network updates in time proportional to its diameter, because that's the amount of time it takes for the marker to reach every node of the network. Okay. So to summarize, we have seen a very simple method for on-the-fly, in-place, and consistent updates. This is the first such algorithm. It actually turns out to be almost trivial to implement. It takes only about 50 lines of P4 code. And what I didn't get into was that the method also supports stateful components like stateful firewalls in a very natural way. Interestingly, it's oblivious to the actual update. So you don't need to do any analysis of the update rules. You can just run the algorithm. And it can be made resilient to temporary failures. We also proved that any in-place and on-the-fly method must drop packets or be inconsistent. And so packet drops are unavoidable. Experimentally, they reduce throughput by 10 to 20%, but we think that by doing some lightweight analysis of the network, we can reduce that number. And finally, for someone who comes to this not from networking, but from formal methods and program verification, it's very nice to see this beautiful distributed systems result find an application to a very real networking problem. So thank you very much.